Alright, how's it going? In the last video, we went ahead and got into the Vasicek model and started our journey of actually getting into modeling. Um, in this video, we're going to continue on with that with the Dothan model, the CIR model, and the Exponential Vasicek model. So, if you guys remember from the Vasicek model yesterday, or not yesterday, last week, the main issue was that it gave negative rates, right? We had Gaussian structure, we had normal distribution, we had tractability, right? The only thing was it was negative rates. And so what we're trying to solve now is trying to keep all the properties that made Vasicek very strong while still solving the positive rate issue. So that's what we're going to try and do. Okay? So we're going to go ahead and start with the Dothan model. And I wrote everything out beforehand just to make things go by a little bit quicker. So the main equation is going to be here. The main thing to take away from this is that volatility is proportional to the level of your short rate. What I mean by this is Vasicek did not have this specific RT value in the Brownian noise component. This is something that is going to be very important, as I'll show you guys later. And also this component right here, which is supposed to be for drift, it's supposed to be for mean reversion. It seems a lot like an exponential growth. Once we go ahead and move from SDE to the actual RT component, as you guys can see, the mean reversion will go ahead and disappear. So we're going to have zero mean reversion. It's going to move towards zero over time. Either that or it moves towards RS, right? Why does it do this? Because T minus S becomes smaller over time. It decays. And of course, we do get the positive structure that we wanted, right? We were trying to solve for that from Vasicek, but we do not get any mean reversion. Keep in mind that the distribution here for the Dothan model will be log normal, right? And if you guys wanted to solve for RT, you guys can go ahead and do it based off of d log RT. And so you would use Ito's isometry, and then you would integrate that from S to T to go ahead and get the same equation here. If you guys want to go ahead and practice this further, of course, there's always going to be the problem sets for every single lecture that I do. So in the past 7 lectures, there has been problem sets in the website, which is in the description of each video. So if you guys want to go ahead and take a look there, it could help you guys out maybe. In terms of the mean and variance, we see it right here, right? Pretty standard. It's close to the Vasicek model, but we got to keep in mind that even though that the mean and variance is close, we still have that log normal distribution. We still do not get any mean reversion. The other issue with the Dothan model is that it is extremely time consuming and complicated to price T-bonds, right? With the Vasicek model, it was very, very simple because we were able to do affine term structure. It was a linear approach. With Dothan here, this is not a linear approach at all, okay? And the reason this is the case is because when you go ahead and take the square of this to go ahead and get your variance, you're ending up with a value that is not linear at all. It's quadratic. And this will be extremely difficult to price T-bonds. If you guys want to see the equation for that, it is on page 63, equation 3.2. So it is still a closed form solution to find that PT, capital T, but it is still extremely complicated. So there is another con of the Dothan model there. And then the last thing I want to talk about is the idea that there is a bank account explosion. So not to be any more dramatic, okay? What this means is that a bank account, if you guys remember, is the primal numerator that we use for all the fixed income. And so in order to kind of find it, right, in order to find the expected value of our position based off of small changes in t, okay, we can think of this as integral, where it's a small change in t, that will be equal to the standard notation of just the integral over rs, right? This was the first thing that we learned in the first lecture. But keep in mind that rs, okay, is log normal, okay? And because of that, it's going to end up with a solution like this. Right? So R of S is your e to the y, where y was your normal distribution property here. Okay. And so when you're doing e to the e, this will cause issues, right? What this essentially means here, okay, is that a small time, at a small time delta t, we can possibly make infinite money starting from 1 unit of currency, right? Because e to the e will explode based off of what y gives. Now this sounds really, really nice, infinite money, right? We all want infinite money, but it can definitely cause issues for fixed income, as we will see in the future. So to summarize for the Dothan model, sure, it goes ahead and makes everything positive by having that exponential form, but it causes a lot of issues. We have no mean reversion whatsoever. Okay, we have zero analytical properties that were still kept. Right, our our T bond pricing is going to be extremely complicated. And to see how complicated it is, you guys can go ahead and go to page 63. So that's another issue. And then the last issue is that it can cause bank account explosions. So our primal numerator can be it can have issues, which is not good once you want to go downstream and look at other derivatives and other measures. So that's the Dothan model. Based off this, we can obviously assume that this will not be used in the practical sense. But of course, the advancements that were made here in 1978 were still extremely important because it led to a bunch of other models, as we will see in the future. So it's not useless, right? It's very, very important still. And so that's where we go into the CIR model, okay? CIR model was kind of developed in 1985, which was 8 years after the Vasicek model. So what it does is that it tries solving the problem of the negative rates of Vasicek while still keeping everything tied together as we wanted. Okay, so the main equation right? This is much more closer to what the Vasicek dynamics was, right? We have this component of mean reversion here. The only difference is that we have the square root of RT for our Brownian noise. Okay. A constraint that needs to be issued is this is called the Feller condition. Okay, so what it means is that it makes sure that the rates that we develop do not arbitrarily move to 0, right? We still have this issue with RT being a component inside Brownian noise. And so it can lead us moving towards 0 like the Dothan model did. And so that's what this property is for. Essentially what it makes sure to do, it makes sure that the parameters have to be chosen such that the mean reversion forces, the mean reversion force away from 0 is stronger than random volatility pushing it around. Probably have to write that out. So the mean reversion force away from 0 has to be stronger than random volatility pushing it. Okay. If you want to go and show the Q0 measure, if you guys remember what Q0 is, it is going to be a real world pricing where there is risk implicit. Okay. So still very, very close to what Vasicek had to offer us before. Right, we have our market measure of risk, lambda. And then remember Brigo and Mercurio make a simplified approach here for tractability, right? The dynamic or the distribution, going back to the risk neutral measure, is non-central chi squared. Okay. Non-central is just the idea that the means of your chi are not going to be centered at 0. They're going to be centered at something else. Okay. Let's see. The mean, of course, we have to show this for any type of model. So very, very close to what Vasicek had as well. And I said this in the last lecture, but if you people want me to write everything down beforehand and then go from there, I'm okay with doing that as well, right? I just don't know if it'll save a lot of time. But yeah, that can definitely be a possibility. So that's the var. Keep in mind that the variance here depends on both your long run mean and RVS. Right, that's something different from Vasicek, which just depended on, I believe, the long run mean. Of course, the great thing about the CIR model here is that it is affine just like just like Vasicek, right? And obviously you guys can see why, right? We have that square root property, but once we go ahead and square that, we go ahead and get a linear approach anyways. So the one thing I do want to show that's pretty important is that if we wanted to model what the T-bond price looked like in terms of the dynamic, let me just go ahead and write that out real quick. So what I'm writing out right now is going to be what Ito does, okay? And then that goes ahead if we wanted to apply it to our specific case. So a lot of writing off formulas and stuff, which you guys can see based off the book. But for those that do not have access to the book, I'm trying to write out as much as I can. Okay. So this first component here is going to be the rate times the specific asset that we have, which is the T-bond. And that's going to be very, very important. The second component is shocks in terms of RT and the current price. And that's what I want to go ahead and talk about. Because the Vasicek model, the bond percentage volatility, the volatility of the bond here, was deterministic, right? So it was deterministic for Vasicek. If you guys remember, it looked like this. But for here, for the CIR, it depends on the state of short rates. Okay, so that will make that'll make things a little more difficult to price derivatives, right? Why does it depend on the state of current rates? Because we have RT, inner Brownian noise, that goes ahead and downstreams into the dynamic of our T-bond. Okay. Last thing I want to talk about is the forward rate measure. So not T-bond, T forward measure. So it was also very, very close to Vasicek as well. So there's a lot of comparison. There's a lot of similarities between Vasicek and CIR. Only difference is, of course, this term here. And then from Gersnoff theorem, which if you guys want to review is, I think it was lecture 4 or 5, I think. And keep in mind that in the website we have all of the lectures, all the problem sets, and all the notes still there. So if you guys want to go ahead and review any previous topics, you guys can go ahead and do that. But yeah, this is the forward rate measure. Of course, we have this term here, which is showing that the drift changes because we are moving to our forward measure. The thing I want to show though is that in a standard Libor market model, okay, in a standard Libor market model, we have a log normal distribution, right? We saw this in, I think it was lecture 2 or 3. Right? So in standard forward rate measures, we have log normal distribution. But it is not the case in CIR, right? In CIR, it's not going to be log normal, it's going to be chi-squared. And because of that, it causes issues with forward rate assumption models. So let me write that down. Not log normal like standard. And I'm sure we'll see an application later on, right? So right now we're kind of just going over literally the models and all the different types of properties, and we're definitely going to be applying them later on, so don't worry about that. But yeah, the CIR model is pretty much the closest that we can get to the Vasicek using time homogeneous and one factor short models, right? We do keep all the properties of Vasicek like affine term structure, we keep tractability, we keep strong mean reversion. The only issues is that we have issues with the dynamic of our T-bond, which depends on short rates. It depends on the state of our short rates, how they also move. And that just makes it difficult to price the derivatives. It's not really an issue, it just makes it more difficult. The T forward measure, the CIR, since it is non-central chi distribution, it is not what we have with the Vasicek model or any other standard market model where this is log normal. And because that, it can also cause difficulties with forward rate measures. Okay. Where's the last one? Yeah. Okay. So that's the CIR model. And then what I want to talk about here is that we have two models now that are part of the affine term structure family. We have Vasicek and we have CIR. Okay. And just to go ahead and briefly overview what Vasicek was again, I know I talked about this before, but this will come up a lot later on. So it's supposed to be an R. Just go ahead and break things apart. And so if you guys remember that spot rate, this is just to show you guys the main property here. Of course, you guys don't need to know the proof and how to simplify this. What it gives us, which is what I wanted to land it on, is that the affine term structure family to price T-bonds, it follows the idea of having a constant plus a coefficient times a variable. Okay, and we talked about this in the last video, so kind of just a refresher. The part I do want to talk about is that what are the conditions exactly to, for example, what are the conditions that made CIR or Vasicek affine, right? And so the conditions is that drift and variance must be affine functions of state variable. Just to simplify that, what that means okay, so what this means is that we need variance to be a property of STD squared. It has to be a linear approach essentially. Same goes with the drift, right? The reason that the Dothan model did not have affine term structure, okay, is because x squared. It didn't follow this coefficient property, right? It had an x squared. It had a quadratic value, and so that will cause issues, right? It had a quadratic value, of course, because we have RT by itself in the Brownian noise, not even a square root over it, just RT. So these are essentially the two properties that are needed. The drift and variance has to be affine functions of the state variable. They have to follow this specific property value. Essentially what it means is that our variance has to be not quadratic. It has to be a squared distribution or a squared value, and then our linear drift has to be linear. Okay, that's basically all I wanted to talk about for the affine term structure. It's just these two coefficients need to be met in order to be affine, which was the case for Vasicek and CIR. And so the last model that we have is the exponential Vasicek model. Okay. And based off the name, basically what it does is we have a regular Vasicek model approach. So right, this is the regular Vasicek model for YT. And so what this exponential Vasicek model does then is literally all it does is that your RT value is going to be equal to E to the YT. That's literally it. And so your YT, of course, is going to be equal to the log of RT. So as you guys can see, there's going to be the property of positive value only. But there's also going to be issues because this is going to be a log normal approach. So it's going to be mirroring the issues that we saw in Dothan. So just to write it out more, we can see then that the actual RT value, or the actual RT dynamic, So the main thing to take away here is that the good thing about this model is that its mean reversion improves. Okay, its mean reversion, as we will see when I write down the mean and the variance, it depends on theta over a. So it does not drift towards zero like Dothan did. It still has it keeps its Vasicek preservation, but we still have this issue right here. Okay, so nothing really changed except the mean reversion property. So writing down the mean. So this is kind of it definitely is a model that is kind of, bootstrapped. All it does is literally just takes a Vasicek model dynamic and just puts e to that equation. So it helps improve, of course, the mean reversion, but it still has a lot of issues. So mean reversion, theta over a. The variance is pretty similar to what this value is, like very, very similar. The only difference is that instead of ln, it's going to have 2 in front, and it's going to have no 4 right here. And that's the only difference between mean and variance there. But yeah, that's literally the exponential Vasicek model. When we're thinking about these model selection questions, right, we have to think about, first off, like, is it positive or is it only positive, or does it allow negative rates? And the question here, or the answer here, is that it only allows positive. Okay, right? We have the E property. But then we have to go into the idea of tractability, or a strong distribution. And the thing here is that this model does not give as strong of tractability as CIR did, right? It still will have the bank account explosion issue. It still will have issues with going ahead and pricing T-bond. It'll still have those issues, right? So overall, based off this entire lecture, CIR model gets the closest to a strong model, right? It preserves the positive rates. It preserves tractability as affine. It has noncentral chi-squared, which is a bit better than Lognormal in the sense that there's not going to be explosions in the bank account. The only two issues, of course, are that the bond volatility depends on the state of your short rates over time, so it can be more difficult to price these derivatives. And of course, the forward rate assumptions can cause difficulties because it is not standard. It's not Lognormal. Yeah, but the Dothan model, there were a lot of issues here, of course. The reason is because we just have RT standing alone inside the Brownian noise. And so when we take the variance, it's going to be a quadratic explosion. And the tractability is terrible here. Even though it's a closed form solution, it is still going to be very, very complicated. And you guys can go ahead and see page 63 if you guys want to see the actual formula for the T-bond. But yeah, those are 3 models so far. In the next video, we're going to go ahead and get into the whole white extended Vasicek model, which really is a strong advancement in terms of moving away from these one-factor models into a new category that practitioners will probably use, right? No practitioner will use a one-factor model for very complicated dynamics in your curve, like steepening or inversion. And keep in mind that all these models as well are time homogeneous, meaning that all of your parameters are fixed. On the other hand, time heterogeneous, which we talked about in the last video, the differences between the two, that can have a lot more different types of complexities and allow for different types of expressions to be made. But, you know, that's what we have going on. Um, but yeah, thank you guys for listening, and look at the website if you guys want to see the problem set or any of the notes in the previous lectures as well.